I'm Brittany Johnson, and today I'm going to talk to you about our paper, Causal Testing, Understanding Defects Root Causes. But first, I want everyone to take a second and think of a bug you recently fixed. Think about your experience and what it took to understand and resolve the problem. Many of us, including myself, just had a nightmarish flashback, thinking about the time and effort that went into eventually fixing that bug, despite having a tool that was supposed to make it easier. We believe that one reason debugging is so challenging is because existing debugging tools, such as Tarantula, typically answer questions like what lines of code are correlated with the failing test that exposes the defect. However, recent work has shown that this information alone is not helpful to developers when debugging. What developers really want to know is what's causing the software defect. So we wanted to know, how can we help developers understand defect cause? To this, we began by exploring existing work on causality and landed on this notion of causal experimentation. Causal experimentation is the process of modifying and executing tests to observe causal relationships and derive causal claims about defect root cause. For example, let's say you're a developer working on some mapping software and you get a bug. From this bug, you'll try and reason about what might be going wrong, starting with maybe the addresses and noticing differences there, or thinking about the path and anything along that path that could be causing problems. Now, as implied, this process, if done, is manual and of course time-consuming. Now, imagine a tool told you that certain inputs failed, but these other very similar inputs pass. Upon comparison, it quickly becomes clear that failing executions start and end in different countries, but passing ones start and end in the same. Therefore, we propose a way of automating causal experimentation, which we call causal testing. Causal testing uses existing debugging techniques, like testing and fuzzing, with the goal of providing minimally different executions that expose defect cause. So, how does causal testing work exactly? Well, let's take a look back at the maps example. Here's our bug, which was found by this failing test. This test has an assertion with a method call and inputs to that method call. The first thing causal testing does is perturb the inputs to the method call and execute these new tests while keeping track of which pass and which fail. Lastly, and most importantly, causal testing determines which of these executions are most similar to the original failing test based on both the input and the execution path. While causal testing is novel, it is inspired by previous work in debugging. This includes work on input minimization with delta debugging, directed test generation, fault localization using observational data, and associating input features with program behavior. In contrast to existing work, causal testing generates new inputs and tests using a manipulationist approach to find executions similar to the original failing. Causal testing can also be used to test software for bias by seeing if, for example, changing gender or race changes outcomes. To evaluate our technique, we developed a proof of concept implementation called Holmes. I will now switch to Eclipse to show how Holmes works. Here we have a failing test, as indicated by JUnit's output. This test takes a hex number as input, but something is wrong. Maybe Holmes can help. We can access Holmes through the pop-up menu here. When I click Run Holmes, Holmes produces the following output. We can see from the passing execution here that the problem lies in the use of an uppercase X in the original input here. Using our prototype, we conducted a user study to determine whether causal testing can help with identifying defect cause and fixing the defect. We also want to know how useful causal testing is. For this evaluation, we compared debugging with Holmes to using JUnit, the gold standard for testing and debugging Java programs. We found that, when using JUnit, participants could correctly identify defect cause 80% of the time, compared to an improved 86% of the time with Holmes. When it came to repairing defects, we found that participants were able to correctly repair defects most of the time with JUnit, with a slight increase when using Holmes. Now, being most Java programmers use JUnit, our goal with causal testing is not to make JUnit obsolete, but to complement JUnit and provide different useful information. And we do, which is fantastic. This is further supported by our usefulness findings, which show that majority of participants either found Holmes more useful than JUnit, citing the similar passing test as the most helpful, or equally as useful as JUnit. A small percentage of participants felt that JUnit was more useful, often citing higher familiarity with JUnit and its interface. But, as we intended, the majority of participants felt that Holmes and JUnit complement each other and both provide useful information for debugging. In addition to whether causal testing can help, we wanted to get a sense for how often causal testing can help. So we manually went through the defects in the Defects per Day benchmark to see when causal testing would work and when it would be useful. Of the 330 defects we manually evaluated, we were able to categorize with confidence 42%. Of that 42%, we found that for 71% of those defects, causal testing would work. This means that a causal testing tool, like Holmes, could find at least one minimally different passing test for the defect. Of the 71% where causal testing would work, we found that for 77% of those defects, causal testing would be useful. This means that the similar tests found by causal testing capture the defect's root cause. In conclusion, causal testing can help developers understand defect cause, plays well with others, and generalizes beyond our user study, as indicated by our analysis of real-world defects in the Defects per Day benchmark. You can check out our full paper for all the juicy details. Thanks for your time.